All right. Today we're going to start the first lecture of chapter number 2. And chapter number 2 is, the title is Motion Along a Straight Line. And the objectives for today's lecture, the first objective is describe a straight line motion in terms of displacement, velocity, and speed. The second, distinguish between average and instantaneous velocities or speeds. And the third is how to make interpretation from the position versus time graphs for a straight line motion. So what we're going to deal with, it's something that we call kinematics. So if you come here and separate kine from matics, it's like mathematics. Mathematics is basically the study of math. So kinematics here is basically study of motion. So that's what kinematic is. So we're going to deal with that. But today we're going to deal with it in one dimension. Later, we will basically extend that to 2 and 3 dimensions. What we're going to introduce today is a vocabulary that we use when we try to study kinematics. And these are velocity, a position, velocity, and acceleration. That's what we're going to introduce in this chapter. But today we're going to only deal with velocity and position and velocities. These are the physical quantities that we're going to introduce in this chapter. So for example, in the image here, you have someone who's basically a bungee jumper. So we can basically describe the motion and so on. That's what kinematics is. Now, we're going to look in one dimension, and we'll choose the x-axis, okay? And we'll try to look at displacement and average velocity, which is basically they're both related with time. Now, as I told you in the previous lectures, when we look at space, we're going to describe it by x-axis and y-axis. And we said the x and the y are basically in the plane of your textbook or the screen as you see them there. Of course, you can go this way, negative y, you can go this way, negative x. But the third, which basically the z-axis, and the z-axis here will be pointing out of the screen or out of the page. Of course, if you go the other way, will be the negative z-axis. So now you can choose either the x, as you study things along the x, or you can study things along the y, or you can study things along the z. And in the previous chapter, we talked about vectors, and vectors will have components in x, y, and z. Today, we're going to look at only one-dimensional motion. So we're going to choose either of these axes, and what we'll start with, we're basically going to choose the x-axis only. So we describe motion along one dimension. Later, we can extend that to 2 or 3 dimensions. So when you do that, okay, if you take your x-axis, you're going to choose a point where we say that this is the reference point. It's equal to 0. Anything to the right, it will be positive. Anything to the left will be what will be negative. Okay. And that's basically how we're going to look at our position in one dimension. So the position is, where are you going to be located? Are you located here, located there? So that's what we call the x coordinate or the coordinate x. And this could be a positive value, it could be a negative value. Positive value, that means you are to the right. Negative value, that means you are to the left of the origin point. That's basically what the position is. Second, we're going to deal with something that we're going to call displacement. And again, you know the meaning of this word. You can take this and you can take the M, E, and T, and you know what a place is. A place is where you put something. A placement, when you basically you place something there. This, that means the opposite. That means you're changing your place. So we're going to look at the displacement, which is the change in your position, or what we say here, the change in the particle's coordinate. And we'll define it as delta x. Whenever you see this symbol here, that means it's a difference. So delta x will equal to x2 minus x1. That means position 2 minus position 1. That's what is a displacement is. So in this textbook, we usually look at the second position relative to the first position. The difference between the second minus the first will give you the displacement. Now, in some other textbooks, you may encounter that they're going to write this as equals x final minus x initial. F here means final, I here means initial. So you may see this. And our textbook here, you will see it a lot as 2 minus 1. That means final minus initial. And this is what a displacement is. And then if you can go between x1 and x2, now you can continue doing that, but you can do it in different times. Even though x1 and x2 are the same, but you can move from x1 to x2 in different times. So how can I bring this in the description? And this is where we say average velocity. And the average velocity here is delta x over delta t, which is the time rate of the change in position. And that's how we incorporate time in. And we call this is average velocity. And that's why we have here, if here means average, and x here, that means you're doing that along the x direction, which is delta x over delta t, which is x2 minus x1 over t2 minus t1. So in this slide here, we're only looking along one dimension, which we call 1D, or a straight line motion, and we only pick the x-axis. You can choose the y, you can choose the z as well, but we pick the x-axis, and we define the position x, and this position x is basically defined relative to some reference point, which is the origin. So it could be positive to the right or negative to the left. And then we talked about the displacement, which is delta x, which is equal to x2 minus x2. Now we can look at the time rate of change of position, which is delta x over delta t, which is x2 minus x1 over t2 minus t1. Is this clear? Any question on this? So now let's just illustrate this with some examples. You have a car here. That's your x-axis. That's the start here. So we're picking position 1. So you can start from here and you start timing. But at position 1, we basically, the time is equal to 1 second. So many of you will say, well, my starting time should be 0. But if you're starting from here and you measure here, so at this point here, your T1 is equal to 1 second, and X1 is equal to 19 meters. So it is positive because your origin is here. That's where the origin is. So your first X coordinate at 1 second is 19. Now you can go to position 2, and you get there after when T is equal to 4 seconds. And your position there is equal to 277 meters. So now you can say, well, T1, which is equals 1.0 second, X1 is equal to 19 meters. T2, which is equal to 4.0 seconds, X2 is equal to 277 meters. Now, so both of my position here are positive. Your time has to be positive. Now, I want to look at the displacement. And displacement means delta X equals X2 minus X1. So if you look at 277 minus 19, that will give you 258 meters. And that's why we say here your displacement is positive, because the displacement is a vector here as well. It's along the x-axis. Now, and then we look at your average velocity, and here you look VFX, okay, which is your average velocity along the x-axis, which is delta x over delta t, which is 258, and delta t will be 4 minus 1, which is 3, and it gives you 86 meters per second. And that's why we say here your average velocity is positive as well. Positive meaning you're moving to the right, or the positive x-axis. In this slide here, we're going to look at a truck, okay, and we basically measure when t is equal to 16 seconds. We see this truck coming from a position x1, which is equal to 277 meters, and at t is equal to 25 seconds, the truck basically gets to x2, which is equal to 19 meters. And in this case, so t1 equals 16.0 seconds, and x1 is equal to 277 meters. T2 will equal 25.0 seconds, and x2 will equal to 19 meters. Now, in this situation here, if I want to look at my delta x, which is x2 minus x1, so in this case, it will be 19, that's your x2, minus 277, and that basically gives you minus 258 meters. And that's why here we say your displacement is positive. Your position is still positive. Your x1 and x2 are still positive, but your displacement is negative. Now, how about the rate of change? Where we're going to look at VFX. F means here average, okay? So the average velocity along the x is delta x over delta t, which is 2 minus 258 divided by 25 minus 16, which is 9, and it gives you minus 29 meters per second, meaning that your average velocity now is negative. If you look at what we did in the previous slide and this slide, you're still in the positive axis, x-axis. Your position are still in the positive x-axis. However, a displacement is a vector. And in the first slide, your displacement was positive. In this slide, your displacement is negative. That means you're moving along the negative x direction. Your average velocity in the previous slide is positive. Your average velocity here is what is negative. That means you're moving along the negative x direction. Is this clear? So now we only took two positions, but in general, you can basically describe your motion by taking a table, and this is your t, and this is your x, and you can basically look at the time and you measure x. So you can say this is t1, x1, t2, x2, t3, x3, and so on. Okay. And once you have that, you can make what we call a position time graph. And this position time graph is the x here will be on what we call the y-axis of the graph, or the vertical axis. Okay. And you say that x and the units for it is meters. On the horizontal axis, or the x-axis, sometimes we always say x and y to present these graphs, you have here the time, and of course the units of that time is seconds. And you draw a curve. Okay. We call this xt graph or position time graph. Now, we may ask you to get the average velocity from this graph. So for example, if I tell you between position 1 and position 2, so you're going to go to position 1 and you find out t1 and x1, and you go to position 2 and you figure out x2 and t2. Now you can look at your displacement, which is x2 minus x1, and the difference in time, which is t2 minus t1. In accordance with the definition that we had in the previous slide, vfx, that means the average velocity along the x, it's equal to delta x over delta t, which is x2 minus x1 over t2 minus t1. Now, if you connect a line connecting P1 and P2, you will find out that actually what you have here is the slope of this line here. So the average velocity, it's the slope of the line that is connecting these two positions. And in this case, it is a positive value. By the way, you can have a situation where you may up getting the difference, and it will be a negative, negative slope, which will be basically going that way. So your slope could be positive, it could be negative. Now, from your graph, you can read. When you have a graph, you can basically read these numbers. Okay. So that's what it means by an average velocity. So when you actually plot a position time graph, the definition of the average velocity will come as being the slope of the line between these two positions. Now, for example, if I choose different positions, okay, so I make now the position closer to one another. Well, in that case, the line that I take, it will become closer to the curve. So as you can note here, that's P1 and that's P2, which is different positions now, but they're getting closer. Why? Because the delta t will be smaller. And you can see that this slope is almost getting closer to your curve. Now, in the second figure here, I make this even closer, and you can see that the line is almost closer to the curve. So if you start basically reducing the time, the delta t, that means you're making delta t smaller, the difference in the position will be smaller. At some point, you may actually, if you make delta t very small, the line will become tangent to the curve. But you're still in the previous slide or this slide, if you take the slope of this line will give you your average velocity. If you take the slope of this line will give you the average velocity. And in this, if you take the slope of this line as well, it will give you also the average velocity. However, if you look at this and this, you're basically, the points are still in the graph. But in this case here, the x1 and x2, they don't have to be on the graph. You're just basically looking at the rise and the run to get the slope of this line. But this line basically is barely touching the graph at a certain point. Now at this point here, this will give me the velocity at this point here, P1 in this case. Now here it will give me the average velocity between P2 and P1, the average velocity between P2 and P1, but here it will give you the velocity at P1. And this is what we call instantaneous velocity. So now, if you look at what we have on the top here, you know what instant is, right? Instant, that means at this instant. Now, you add to it instantaneous, that means I want to look for the velocity at a certain time, not the average velocity between two different times. And graphically, what it means that you pick the point that you want and you draw a line tangent to it, and you take the slope of that tangent, and that will be your velocity or instantaneous velocity at that point. So now our definition of instantaneous velocity, we call it Vx here. Remember, we don't see the Vf here, we don't use it anymore. F, that means between two different locations. But now I'm looking at one instant, at one time, not two different times. And x here, that means it's the x component. And it's the same definition, delta x over delta t. But I take it in the limit as delta t tends to 0. Not equal to 0, but it tends to 0. That means very close to it. That means I'm taking a very small interval. And this is where I say that this is equal to dx by dt, which is the derivative. Okay. So an average velocity, it is taken between two different times. Instantaneous, that means you're doing that at a certain time. And the definition of average velocity is delta x over delta t, but the definition of instantaneous velocity, which is Vx, is dx by dt. And that's how you obtain this from a graph, and that's how calculus works. Is this clear? So far, we basically talked about position, which is x, and then we talked about displacement, which is x2 minus x1, and then we talked about v of x, which is average velocity, which is delta x over delta t, which is x2 minus x1 over t2 minus t1. And then we talk about Vx, which is instantaneous. And this is equal to dx by dt, which is basically the limit as delta t tends to 0 of delta x over delta t. So now we introduce the x coordinate, which is position x, displacement, which is the difference between the two positions, and then average velocity, and then instantaneous velocity. So that's basically how we look at average and instantaneous. In this graph here, now we're going to deal with instantaneous. So they give us an x time graph. Now your x could be positive or negative. Now many of you we put it here vertical. That doesn't mean, because you're all familiar that x always in this direction, but when I brought it, I can make it this way. But time t is greater than 0. You don't have negative time within our definitions here. So what happens is that's the time, and the x could be positive or negative, and that's your curve now. You have a curve like this. You start from t equal to 0 and you go to some other time. They ask us here is to describe the motion at different location, at A, at B, at C, at D, and at E. So now I want to look at a motion diagram. Now, if I want to look at my velocity at A, I have to draw a line which is tangent to A, and I get the slope of this line. And you'll find that the slope of this line here is positive. That's why we say that Vx here is greater than 0. If you come to point B here, you draw a line which is tangent to B, and you take the slope of this line. Of course, the rise here is bigger than this one, and delta t here may be smaller than this one. That's why you have a bigger value here. And we say that also in this location that Vx is greater than 0. So in my motion diagram here, where now this is my x-axis, and this is the reference 0 on my x-axis. Now at t is equal to 0, my v here is represented by a vector. The length of this vector here tells me how big is my velocity. And that's why from here we have this Vx. Now at t is equal to 0, at this point here, my velocity, now you can see the vector is bigger because the slope of this line is going to be bigger. But it's still, my velocity is positive. That means it's moving toward the positive x-axis. Even though if you look, you are x that you're looking at, it's in the negative x direction. That's the position. But at that your position, velocity is going toward the positive x-axis. When you come to point C and you do that, the slope of your line will be 0 because it has no rise at all. And that's why here, when we come to at x at this point here, we say that Vx is equal to 0, and you don't see any arrow here because it doesn't have any size, because its magnitude is equal to 0. Now we come to point D, and when you come to point D, the slope of this line now is negative. It's pointing toward the negative x-axis. And that's why here you calculate the slope, but your slope or your vector now is pointing toward the negative x-axis. And when you come to point E, the same thing. Your slope is negative, but it is smaller than this one, and that's why you have a smaller length for the vector here. And that's your motion diagram now. So when you're talking about Vx, it is dx by dt. It is the derivative. Okay. Is this point clear? So that's basically how you calculate your velocity or instantaneous velocity from an xt graph. So in the previous slide, we differentiated between two things. We differentiated basically between v of x, which we said it's delta x over delta t, and Vx, which is equal to dx by dt. This is average velocity, and this is instantaneous velocity. But when it comes moving between two different positions, we talked about displacement, and we said that delta x is equal to x2 minus x1. Now, you may actually wonder if you start from x1 and then you move 10 meters and then you come back 10 meters. Now, if I ask you about the displacement here, okay, you will tell me if you take x1 here, let's say to be equaling, let's say 5 meters. So x here will equal to 15 meters, but when you come back, x is equal to 5, x2 is equal to 5 meters. So your displacement here will equal to 0, because it will be 5 minus 5, which is equal to 0. And to some may say, well, my displacement is equal to 0 because I am ending up at the same location, but I move. Okay. And this is when you're going to talk about distance. Okay. So if you are at the same position and you did not move at all, well, you have a displacement of 0. But if you are at the same position and you move and you end up at the same position, your displacement is equal 0. So you say, as if I did not move, but I made a movement. Now you have to come in the distance. You basically, distance is how much did you move. It's not basically a displacement. And this is the difference now. You can take position A as you have here and position B, and you go from A to B, your displacement is B minus A. But you actually may have gone this way here. And that's a longer distance than this displacement. So if this is B is 10 and A is 5, so the displacement is 10 minus 5, and it's equal to 5. But if you look at how much did you move in displacement, you'll find it's bigger than 5. So the distance is the length of the path it traveled, and it's a scalar quantity. Displacement is, on the other hand, okay, is a vector quantity, and it's only the difference between the two positions. So in this situation here, your displacement is x2 minus x1. That's your displacement. Your distance also, what you traveled here. And you will find out that distance is always positive. So in this case here, your total distance is the absolute value of your displacement. Meaning, if you move from x1 to x2, so it's x2 minus x1, which will be a positive value in this case, and it's equal to your displacement. But what happens if you move from x2 to x1? Well, x2 is a bigger position than x1, so the value is negative. So your displacement is negative, meaning that you're moving in the opposite direction, but the distance will be the absolute value of there. And that's why we say that the total distance should be the absolute value of the displacement in this situation here. But what happens if you are moving from x1 to this point, and then you're coming back to x2? Now, in terms of displacement, that's your displacement here. It is x2 minus x1. But in terms of distance traveled, you basically move this way, and then you can make that this way. The distance that you travel is much bigger than the absolute value of your displacement. And that's why we say here that the total distance is greater than or equal to delta x, the absolute value of delta x. This is the situation where the total distance is equal to the absolute value of delta x. But in a situation like this, that's when your distance is greater than delta x, or the absolute value of delta x. So you really have to consider the movement along the positive and the movement along the negative, and that will give you your total distance. So you should distinguish between distance and displacement. Distance is the length of the path you travel. Displacement is basically the difference between the two positions. Is this clear? So this is basically where you're going to deal with your distance and displacement. Now, we already dealt with average velocity, which is equal to delta x over delta t. Now, there is something that we call average speed, okay? SM, and we use S here, not V, okay, to distinguish that we're talking about speed. Okay. An average distance is equal to delta total distance by total time. So if you go back to the previous slide, we have a situation where we may have the distance and the displacement equal. That's only if you're moving along the positive x-axis and you have this. But in most cases, your distance is bigger. So your average speed, it may be equal to your average velocity, but usually it's different. And you should distinguish between average velocity and average speed, because many people sometimes they talk about speed. And average velocity and average speed are not related. And in many cases, your average speed is greater than your average velocity. And that's always the case. Because when you're talking about your average speed, you're talking about the total distance divided by your total time. That's probably a situation where you can have average speed and average velocity are equal. But in this situation here, no, that's not going to happen. So average velocity and average speed are not related. Is this point clear? Now, the second point that we want to address here is what we call speed and velocity. And when we talk about speed and velocity, now we're referring to instantaneous. So we're talking about instantaneous velocity, instantaneous speed. Okay. Now, instantaneous velocity and instantaneous speed, well, if you look at when we talked about instantaneous velocity, we said that the difference delta x is very small. So it's almost going to be the distance. And that's why when we talk about instantaneous speed, you don't see an arrow on the top here. If you do not see this arrow, that means you're talking about speed. It is the absolute value of your velocity. Your velocity could be positive or negative, but your speed is always positive. It just gives me the magnitude. So the speed is the magnitude of velocity. But in this case is the instantaneous. So average velocity and average speed are not related. But speed and velocity, they are related. The speed is the absolute value of the velocity, meaning it is what it is, the magnitude of that vector. Now, in 3 dimensions, the vector should have an x component, y component, and z component. And remember, we said always I hat along the x, j hat along the y, and k hat along the z. But in the present lecture here, or in this chapter, we're only talking about motion along one dimension, and we choose that to be along the x-axis, so we're only dealing with the x component here. And that's why we're not writing the I hat. Okay. And that's why we write Vx. So in this situation here, in 1D, the V here with no vector sign on the top, meaning speed, it will be the absolute value of Vx. And this is basically the vocabulary on the concept for today. We talked about position, x. We talked about delta x, which is x2 minus x1, and we call this displacement. And then we talked about vf that x, which is delta x over delta t, which is x2 minus x1 over t2 minus t1. And then we talked about Vx, and we said that the Vx is equal to dx by dt. Now, V, it's the absolute value of Vx here. And that's basically our speed. But average speed is total distance divided by total time. And of course, the units of position is meter, and the unit of time is seconds. So position is in meters, displacement is in meters, but velocity, average velocity is in meters per second. Instantaneous velocity is in meters per second. Instantaneous speed is meters per second, and also average speed is in meters per second. Are these clear? Are these concepts clear? So let's illustrate that by an example here. And the example here, it tells you at t is equal to 0, a cheetah starts running at 20 meters to the east of an observer toward an antelope which is 50 meters to the east of the observer if the position of the cheetah changes with time in accordance with the following equation here. x is equal to 20 plus 5t squared, where x is in meters and t is in seconds. The first question is, find the theta displacement between t equal 1 second and t is equal to 2 seconds. Well, your displacement, it's x2 minus x1. So x2 is evaluated when t is equal to 2 seconds, and x1 is evaluated when t is equal to 1 second. So let me go to my equation here. For x2, I'm going to put 2 for t, and that's why it's 20 plus 5 times 2 squared, and 2 squared is 4, and 4 times 5 is 20, and 20 plus 20 is 40. Now, when you come to x1, you're going to use t is equal to 1, so it's 20 plus 5 times 1 squared, and 1 squared is 1, and 1 times 5 is 5, plus 20, it's 25, so you have 40 minus 25, okay, and that will give you 15. So delta x here is equal to 15, it's positive. Now, your average, find the average velocity between 1 second and 2 seconds. Well, Vx is delta x over delta t, which is 15 over 2 minus 1, which will give you 15 meters per second. And that's basically your average velocity here. Now in C, find the instantaneous velocity at t is equal to 1 second. Now it's different. Okay, average is between 2 different times. Instantaneous at a specific time, and we choose the time to be at 1 second. So basically the Vx here, it will be dx by dt, which is d by dt of 20 plus 5t squared. Now the differentiation of t squared is 2t. So and the differentiation of 20, you don't have a t here, so it's 0. So you get nothing. You get 0 for 20. And here it will give you 2t times 5. You will get 10t. And if you want to evaluate that at 1 second, so you're using 1 for t, and that will give you 10 meters per second. That's now your Vx. Now I can add V, by the way. And you know that V is the absolute value of Vx, which will equal to 10 meters per second. So V here is speed, but here Vx is your velocity. And velocity is a vector, but since we're dealing only in one dimension, we're only dealing with the x component. Is this example clear? Any question on this one? So that's basically how we deal with things like that. Now in this example here, they will give you an xt graph. So you have x, and the units is meters. On the x-axis here, you have t, and the units are seconds, and they give you this graph here, and they give you different points: A, B, C, D, E, G. And the first question here, the average velocity between t 1 second and t is equal to 6 seconds. So if I go to my average velocity, which is equal to x delta x squared over delta t, which is x2 minus x1 over t2 minus t1. Now x2 happens at t2, and t2 is 6 seconds, so I go to 6 seconds here. Well, at 6 seconds on the graph, my x is equal to 0. So x2 is equal to 0. And x1 happens at t is equal to 1 second, and at t is equal to 0. So it happens here, and your x is equal to what? Is equal to 20. So your displacement is x2, which is 0, minus 20. divided by the difference in time, which is 6 minus 0, and it gives you minus 20 over 6 meters per second. So again here, at t equal to 0, x1 is equal 20. At t is equal to 6, x2 is equal to 0. Your v of x will equal to x1 minus x2 minus x1 over t2 minus t1, and that will equal to 0 minus 20 over 6 minus 0, and it gives you minus 20 over 6, and it gives you minus 3.3 meters per second. And that's now your average velocity between points between 0 and 6 seconds. The second question here, and I will do B and C in one, the instantaneous velocity at points A, D, and G. And C, they ask about the instantaneous speed at point A, D, and G. And remember, I told you that the instantaneous velocity is the absolute value of the velocity. Instantaneous speed is the absolute value of the velocity. So once we find out the instantaneous velocity in B, we just take the absolute value, and that will give me my instantaneous speed. So now, if I want to do that at point A, now you have to draw a line tangent to A. So you can see you want to take the slope of this line that passes through A, the green line here, that passes through A. You want to take the slope. You can pick any 2 points on this. Now, it's a lot easier for us to pick points here on the graph. So I will take at 0, and I will take the point at 3. So at t is equal to 0, I get 20 for x. And at t is equal to 3, I will get 40. So the Vx at A will equal to x2 minus x1 over t2 minus t1, 40 minus 20 over 3 minus 0. And I get 20 over 3, which is 6.67 meters per second. That's now my velocity. Now, if I want to get my speed, and you know that the speed VA here will be the absolute value of Bx at A. And that's why the VA here will equal to 6.67 meters per second. That's the speed now at A. Then they're asking me to do that at point D. Now at point D, I will draw a line which basically pass or tangent, so it will pass through D. Now it's a lot easier for me to use this point and this point here. So at t is equal to 5, my x is equal to 40. At t is equal to 6, my x is equal to 0. So it is 0 minus 40, because it's always x2 minus x1, divided by 6 minus 5, which is 1. So it's minus 40 over 1, which gives me minus 40 meters per second. And that's my Vx as D. But my speed, Vd, is the absolute value of that. It will be 40 meters per second. Again, at G, I'm going to draw a line which is tangent to G. And you know that this line doesn't have any slope. So the velocity x at G is equal to 0. And of course, the speed also is going to equal to 0, because the absolute value of 0 is 0. Finally, here, they ask about the average speed between t0 and t6 seconds. Now, they ask about speed, not velocity. Now, we did the average velocity between 0 and 6 here, and we found the average velocity, it's equal to minus 3.3. Now here, we're looking at the average speed, and the average speed is total distance divided by total time, and your total time is 6, because you're going from 0 to 6. But the distance now, you really have to look at the total distance traveled. So you went from 0 to, from 20 to 40. That will give you a difference of 20 meters. So you moved from 0 second to 3 second, you basically achieved 20 meters. But between 3 and 5, you were actually at that location. You did not move. Your position stays the same as 40. So you're achieving 0. And then you move between 5 and 6. You moved from 40 to 0, and that's 40 meters. So your total distance will be 20 plus 40, which is equal to what? It's equal to 60 meters. We have it here in more details that the interval between 3 and 4, you're basically getting 0. But between 0 and 3, you get 40 minus 20. But you have to take the absolute value of that because it's a distance, so it's 20. And between 5 and 6, it is 0 minus 40 because x2, but you take the absolute value of that and you get 40, so your total distance is 60. And if you divide 60 by 6, you get 10 meters per second. That's your average speed now. Your average velocity was minus 3.3 meters per second. And you can see here that your average speed and your average velocities are not related. Is this clear? Let's deal with some questions here. You throw a ball up to a height of 20 meters. You catch it 2 seconds later. You catch it, that means it comes back. So it's one-dimensional motion. But you throw things up, so we're going to use this as the y-axis. Remember, we talked about the x-axis. That's the y-axis now. Okay. And if you look at your y1, it's equal to 0. And your y2 also equal to 0 because it will come back to you. So your delta y here, which is y2 minus y1, will equal to 0. Which will give you your average velocity along the y, which is delta y over delta t is equal to 0. But if you look at your total distance traveled, you went up 20 and you come back 20, so your total distance is equal to 40 meters. And your average speed will equal to 40 over 2, which is 20 meters per second. So you can see that your average velocity is 0, but your average speed is 20 meters per second. And we differentiated between displacement and distance here. In this problem, a cat runs along the x-axis from A to B. That means it's moving, if we choose A to be 0, that you're moving in the negative x direction. And then from B to C, the distance between A and B is 5. The distance between A and C is 5 meters. That means if I choose A to be 0, my starting point, then C is basically at minus 5. The distance between B and C is 10. So from B to C is 10. Relative to A, XB will be minus 15 here. Now, the time to run from A to B is 20 seconds, and the time to run from B to C is 8 seconds. So they go 20 seconds, then it comes back in 8 seconds. So in total, you have 28 seconds. What is the magnitude of its average velocity? Now, you know by definition, average velocity is delta x over delta t, which is x2 minus x1. Your x2 is here, which is minus 5. And your x1 is 0. So it is -5 minus 0, and the time is 28, because 28 minus 0, so you get -5 over 28 meters per second, and that's basically your average speed, average velocity along the x-axis. Now you want the magnitude, but they ask about the magnitude here, and magnitude is you're taking the absolute value of this, and that absolute value of -5 over 28 will give you 5 over 28 meters per second. In the part B, they ask you about average speed. Average speed is total distance divided by time. Your total distance is basically 25, because you go from here to here, which is 15, and then you come from back to C, which is another 10. So 15 and 10 will give you 25. And if you get your average speed, it will be 25 over 28 meters per second. In this question here, they give you an x time graph, and they ask you at which point is the Vx greatest. So if you look at point B and you draw a line tangent to B here, and you take the slope of this line, it will give you a positive value. So the Vx here will be greater than 0. And if you go to point Q here and you draw a line which is tangent to it, it will give you Vx is equal to 0. The same thing will happen to at X. It will give you Vx is equal to 0. But here you draw a line which is tangent to this, and it will give you a slope, but the slope here will be negative. So Vx will be less than 0. And they ask you here, when is the velocity greatest, the Vx, and it will be at point B, because that's the positive value. Now, they ask you differently here. They ask you about the speed, when the speed is greatest. Now, we know that the Vx here is greater than 0, the Vx here is equal to 0, the Vx here is equal to 0, the Vx here is less than 0, but V is the absolute value of Vx. And you will find out that here, if you take the absolute value of the Vx here, it will be bigger, because here, less time, bigger rise. Here is bigger time and maybe less rise if you want to compare the two. And that's why we say here that the greatest speed happens at point R. And that's the difference now. When we talked about velocity, we said, no, the greatest velocity is point P. But when we talked about speed, we said, well, the greatest speed is basically at point R. Is these points clear? Now, in this question here, they give you an XT graph. That's how car 1 is moving. That's the curve for car 1, and that's the curve for car 2. And they want you to answer these questions. At which time do the two cars pass each other? Well, they will pass each other at the same time, right? And the only way this will happen if they basically at this point here. So they will do that at point D here. Now they ask you at which time, if any, does car 1 momentarily stop. So you look at car 1. If this is x and t, and you take the slope and you find velocity at car 1, never have velocity of equal to 0. So you will say at no time, okay? So there is no time when it will stop. But if you look at car 2, this is where you can basically have the Vx here is equal to 0, and that happens at point C. So you say here at C. At D, at which time are the cars moving with identical velocities? Now, car A will have the same velocity because the same slope. Car 2 will have different velocities, but you will look for the slope or the point that will give you the same slope as this one, and you will find only this portion here, which is parallel to this, and that will give you the same slope. So you'll find that at position A here, that's when the two cars have identical velocities. Okay. Is this clear? Is this clear? So that's basically what we want to do. An exercise that you have there, you can do it later, but we can go through it very quickly. You're given that x, it's equal to minus 4t plus 2t squared. Find the average velocity between t0 and 2 seconds. So it is x2 minus x1 over t2 minus t1. So you're going to evaluate x at 2 seconds minus x at 0, and you divide by that. And you will find out that basically it will give you 0 minus 0, and you will get 0 meters per second for your average velocity. Then they ask you here about average speed. So to get the average speed, you want to know how much did you move to the positive, how much did you move to the right. So if you want to know, did you stop in the trip when v is equal to 0? So if you take the Vx here, which is delta x by delta t, it will give you minus 4 plus 4t. And if you equate that to 0, that will happen only when t is equal to 1 second. And this is where you have to be careful. Okay. So at t is equal to 1 second, you stop and you come back. So what you're going to do is you want to calculate your distance to 1 second, and then you come back with 1 second. And if you put 1 second in this equation, it will give you minus 2. Okay, and that means you're going back and forth. That will give you a total of 4 meters, and if you divide that by 2 seconds, and it will give you 2 meters per second. So you have to be careful when you're dealing with something like this. So today we only introduced the motion in terms of position, displacement, velocity, and speed. We looked at the difference between average and instantaneous velocities and speeds, and how can we get information from an XT graph. Is this clear? Any questions? Good.